Most of the time when you're calculating a derivative, you don't want to refer back to the definition of derivative because that would involve calculating a limit that could be kind of complicated to do. And that would take a little bit more time. So instead of doing that every single time, you want to create and remember those rules that can be applied to many different situations, that instead of having to refer to limits every time, we can refer to those rules of differentiation, as we're going to call them. So the first and easiest rule to come up with and understand is the constant rule. So let me make a drawing. This is saying that the derivative of a constant c equal to 0 for any real number c. That makes perfect sense if you imagine the function y equal to c. So this is the graph of the function. This is a horizontal line. The tangent to this line is its own line. So any point that you choose, the line that's tangent to that line is the same line, right? And that line has slope 0. It's horizontal. So that makes perfect sense that the derivative is 0, which is the slope of the tangent line. So how do I actually prove this formally? So I use the definition, and I'll do this only once. After that, we're going to start using the constant rule every time I have to derive a constant. So this one time, we're going to calculate this derivative using the definition. So the definition, first I have to see what my f is. F of x equals c. And then f prime of a is the limit when x goes to a of f of x minus f of a over x minus a. So that's the definition of derivative. So then I plug things in. What's f of x? That's c. So c minus, what's f of a? That's also c. X minus a. So that's the limit as x goes to a. So this is c minus c. That's 0. The top of a fraction equals 0. 0 divided by x minus a is 0. Note that I didn't plug in x equal to a yet. I found 0 before plugging it in. 0 divided by anything equals 0. Now when I plug in a, I don't have to plug it in because it's just a. So it's just the limit of a constant. The answer is just 0. So that is the proof, right? So the constant rule is telling me that the derivative of any constant equals to 0. Now the power rule is a more complicated proof. We're going to proceed the proof and do the proof in the same way. What this is saying is that whenever you derive x raised to some power, the result is the power times x raised to the power minus 1. That's how I remember it. The power times x raised to the power minus 1. So how do I actually prove this? So same thing. I do the limit when x goes to a, right? So that's going to be my, let me write it more carefully. So f of x equals x to the nth power. Then f prime of a, by definition, is the limit when x goes to a of f of x minus f of a divided by x minus a. So that will be the limit when x goes to a, x to the nth minus a to the nth, x minus a. And now, to actually cancel out, factor out something from the top to cancel out the x minus a, I have to refer to a special product. So maybe you remember a special product that we use all the time that we call the difference of squares. So that will be x squared minus a squared. That equals to x minus a times x plus a. Maybe you've seen that before, likely in a pre-calculus course, or even when you started studying calculus, you saw this again. This is a special product that we use all the time. We call it the difference of squares, but it's actually a special case of a more general idea, right? You see the similarity. This is x to the nth and a to the nth. So it could be x cubed minus a cubed, or x to the fourth minus a to the fourth. So the general rule is this: x to the nth minus a to the nth equals to x minus a. So it starts the same way, but then this is going to change. This is going to be x to the n minus 1. So 1 power less than what you had here. And now you add the terms by every time you create a new term, you decrease the power of x. So x n minus 2. And you increase the power of a. So a. The next one is decrease the power of x, x minus n minus 3, increase the power of a, so a squared. And the same one, decrease the power of x, n minus 4, increase the power of a. So you're going to keep doing that until the last term will be just the same power as you had originally at the beginning, but then with a, because all x's will have disappeared by then. Okay? All right, so there's n of these guys. So if you count them, just like with x squared, there were two terms, right? There's one term here, another term here, right? One term, two terms. With x to the nth, there's n terms. So if you count them all, you're going to see that there's n of them. How many terms it takes for, by decreasing one at a time, for the x to disappear. Or you can count like maybe the powers of a, right? That's a to the 1, 2, 3, dot, 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 until n minus 1 a's, and then plus this extra term without a. So you can count it that way. This is going to be important because we're going to apply this rule to our proof. To do x minus a, then I'm going to copy part of it. The last one will be a to the n minus 1. All that divided by x minus a. So you can cancel these two out. That's what I wanted originally. And then finally, what I do, now there's no restriction in the denominator for plugging things in. Is I plug in a. So direct substitution property, this is a continuous function, it's a polynomial, so I can just plug in a. So I get a to the n minus 1 in the first term, plus a to the n minus 2a, so what is this, right? This is a to the n minus 1, there's no change. The second one is a to the n minus 2 times a, so I add n minus 2 plus 1, so that's n minus 1. The second term, the same thing will happen. So look at this, the third term actually, right? This x is going to become an a, so this will be n minus 3 plus 2. So that's going to be n minus 1 again. So I'm adding all of these terms, but they're all equal. And like I said, there's n of them. Just like in the x squared case, there were two of them. There's n of them. So there's n, a, n minus 1. So that's exactly what we were talking about before. So the derivative at a is power a raised to power minus 1. This is the proof. Put my little square here as an indication that we're done with that proof. This is good policy when you're done with proofs to indicate that you're done. But we're not going to be doing this proof all the time. We're just going to be using the result of this rule. So how do we do that? These are the examples. So a is asking what's the derivative of x to the 9th power, or by the power rule. This is power x raised to the power minus 1. So that's 9x to the 8th power. So that's the answer. That's the derivative. I don't have to do a limit and compute things, divide stuff, use special products, complicated special products. I don't have to do that, because I already remember the power rule. What's the derivative of x? So that's the same thing. So this is the derivative of x to the first power, so n equals to 1. So I bring the power down. So power x raised to the power minus 1. So that's 1 times x to the 0th. So that's just 1 times 1. So that's just 1. That's the derivative. Okay, c. c will be the derivative of 2 to the 8th power. That's where many people will make a mistake. So the first idea that would come to mind would be, okay, there's a power, so I'll use the power rule. They'll say this is power 2 to the power minus 1. So that's 8 times 2 to the 7th, but that's not true. That is not true because there's no x involved. The fact that there's no x involved means this thing inside is a constant, right? whenever you try and plug an x into this expression on the inside, you get the same value, which is 2 to the 8th, right? 2 to the 8th is actually a number that you can calculate. 2 raised to the 8th power equals to 256. So this function, if you were to graph that, that would be a horizontal line at y equals 256. So the slope of that guy is 0. It's the derivative of a constant. Okay? So this is a common mistake. Pay attention to that. Don't fall for it. I hope this was a good video that helped you understand both the constant rule and the power rule for derivatives.